This is an example for problem 223. Deals with the two-dimensional Taylor series expansion, so two-variable expansion Taylor series. So the function they ask us to find the expansion of the equivalent Taylor series is sine x cosine y. So the base Taylor series tells us first to write down the functional value at the point of origin. In this case, the point of origin is defined for us as 2, 2. So instead of x and y, I just replace that with sine 2 cosine 2. And that's kind of where these parts over. So that would really be your root term, or the point of departure. If that was the origin, many times that might actually be a 0 value. Maybe, who knows. We go with the leading coefficient over the next term. So 1 over 1 factorial, super exciting. But this is where we start dealing with deviation. X minus x naught. That's the distance you are away from that point the derivative was taken at. So in this case, x naught is 2. So I'll have x minus 2 times df dx. So the derivative of the function taken with respect to x at, I'll adjust the parentheses a bit to make this a bit more legible, at x naught y naught, which for our case is 2 and 2. So in our case, the derivative df dx just results in a function of cosine 2 cosine 2. But we're still not done. You have to now do the y dimension for this first derivative level, plus the new y location minus y naught, which was given to us as 2. Now we do df dy at x naught y naught. So the solution in that case would be sine 2 sine 2. The derivative for df dy at 2 2 is sine 2 sine 2. So that would finish up all of the first derivative terms, and now you'd move on to the second derivative. So let's just go ahead and make a second row about it, summing things up, and now you'd actually do 1 over 2 factorial, which is again thankfully an easy one to figure out. Do the same thing here, your deviations, x minus 2, and now you're dealing with the second derivative of the function taken with respect to x. So the second partial with respect to x, numerically sourced about 2 2. So the derivative of the derivative of the functional value taken with respect to x becomes sine 2 cosine 2. Then we go with the deviation, again for y. Deviation away from the point we've sourced the derivatives at. And then this second derivative for that location becomes sine 2 cosine 2. One additional term that comes into the second order write-up, the second order derivative, is now you have the intermediate, kind of the inner terms, if you will. So we'll add 2 times x minus x naught, which in our case is 2, y minus y naught, which again is 2 because we started at the origin, or at the point 2 2. And then now this is the second derivative, the functional derivative df dx dy. So taken once with respect to either, and that comes out to be cosine 2 sine 2. And that should be a decent approximation out to second order of f of xy equals sine 2 cosine 2, or sine x cosine y, more precisely. That is the Taylor series expansion out to the second order. And this is really just following verbatim equation 278 in your textbook. So if you ever encounter a problem like this on an exam, that's exactly where you should probably go first to source the required information to solve it.